Okay, today we're going to talk about the image processing pipelines in digital cameras. It's kind of a lot of the core of the technology in digital photography is how you process the images. And there's a whole lot of material there, so again, today's lecture is kind of a quick overview of that, and we'll have a lot of open topics we can talk about at the end of stuff to maybe get into later. There's a number of books here from which I've drawn ideas, inspiration, data, and figures, and the one in the upper left there by Hunt is sort of the Bible on color. It tells you all about how color works and why color matrixing is necessary and strategies that have been employed in different systems like television and photography and so forth over the years. You've seen the one in the middle several times before. I keep bringing that one up. The one on the right, Digital Color Imaging by Sharma, has got a really good chapter on image processing pipelines from which I've drawn a few figures, and I'll be talking about that one. And then the one on the bottom, Technical Introduction to Digital Video by Charles Poynton, is a good source of data. It's got all the matrices you need to represent different color space standards and things like that. So this book, the Sharma book, has this chapter by Ken Perelsky and Kevin Spalding. These are a couple guys that I got to know a bit on some of the standards committees, and they've done a lot of work to sort of develop good methods for image processing and to propagate those through standards and books and writing and stuff. And it's a lot of good details in that book. So one of the figures, or two of the figures in that book, are these simplified pipeline diagrams that show you what happens in a consumer camera and in a professional camera. The difference between them is what's the output, basically. So the consumer camera outputs JPEG files, and the professional camera in this conception outputs RAW files. So the question is really how do you organize the different stages and where do you do storage and so on. But in terms of what the processing is to make a picture, it's more or less equivalent in the two cases. There's a lot of optional steps, and the number of steps in a typical pipeline is actually greater than what you see here, and the professional cameras are likely to have more steps than the consumer cameras and so on. So we'll get into what some of those other steps are. I want to go back and start at the sensor where we were last week and talk about what goes on chip before you get the data. In the high end, there's a on-chip amplifier, but not the A to D converter, and in the lower end, the A to D converter is often integrated on the same chip with the sensor as well. And these amplifiers can have a lot of different features. For example, the correlated double sampling I talked about, which is a thing that removes certain kinds of noise, reset noise, KTC noise, which may be one of those, or in a CMOS amplifier that may be one per column. You can have multiple amplifiers, for example, for the two sides of a big chip, or some of the new sensors in the new Canon camera, I think, has 8 tap readout, something like that. So it's like it's reading out the sensor as 8 sensors in parallel. Or in the Foveon chips, you tend to have a channel for each of 3 colors, or you can have more, different ways of organizing output taps and amplifiers. Some of the chips have an optional, or it's not optional, some of the chips have and some don't have a programmable gain associated with their amplifiers. Some of them are fixed gain. So the software controlling the camera can increase the gain or decrease the gain if that optimizes the performance for different ISO speed settings and so forth. And in many cases, there's also an off-chip amplifier between the sensor chip and the A to D converter. So next thing that happens is you convert those analog signals to digital. Some of the ADC chips are sort of complicated analog front-end chips that they call them, have a thing called a black clamp. That looks at the leading pixels on each row, which are coming from a light-shielded area on the sensor. And they take the level there as a black reference, and then they try to get black in the right place. In my experience, that's not all that common. You do find it on A to D converter chips, but it's not all that common that it's actually used in cameras because it has certain problems in terms of the way it adapts. It can add some row noise and things like that. These converters typically will go at least 10 bits in the low end and 14 bits or more in the high end. They're reasonably linear, around 10-bit linearity. The extra bits are not usually worth a whole lot, but sometimes they are. And at the A to D converter, you sometimes will immediately follow by a lookup table. And that can either be to to linearize the response in a CMOS chip. CMOS chips are not as linear as CCDs because the charge to voltage conversion is being done on the capacitance of a diode, which is a nonlinear device. So you get a little bit of a compressive response there, and for some of the subsequent steps, you want the processing to be pretty linear. So you may have a lookup table that linearizes the response so that the digital numbers you're working with are in a linear relationship to the amount of light instead of a slightly nonlinear relationship. Sometimes you'll also have a lookup table there for other purposes, for example, to impose a nonlinearity to make the data compress better to fewer bits. Or you may go straight into a lossless or nearly lossless encoding to store raw data at that point. So here, for example, is a case where you might put a gamma curve right on the raw data coming out of a sensor. If, for example, you have say a machine vision camera of some sort that wants to communicate back to your PC over an 8-bit channel, but it has a 12 or 14-bit A to D converter, you can ask what's the best way to squeeze that data down to 8 bits. And there's lots of fancy, clever ways you can compress the bandwidth down, but if you really just want 8-bit samples through a lookup table, what's the best lookup table? And the thing that works pretty well there is to make the quantization steps at all parts of the intensity range be in the same proportion to the noise at that intensity. And so the slope at the bottom end of the curve here is determined by the read noise of the sensor. You want a lot of counts per light intensity when the noise is pretty small. It's just the floor, the noise floor there, which is about 30 electrons in an example sensor. And at the high end, where you're up around, say, 58,000 electrons, the square root of that is the number of electrons of shot noise, around 240. So it's 8 times as much noise up at the high end. So you can use 8 times as big a quantization step and get sort of equal amount of degradation to your data. So here with only 8 bits, you can keep the quantization step size about the same size as the noise, which means it doesn't really add very much to the variance over the entire range. So if you need to cram 12 or 14-bit data through an 8-bit pipe, that's one very easy way to do it. Okay, so this graph shows the, I'm sorry, I didn't label it. In fact, I clipped the numbers off the axes because they weren't right. On the horizontal axis here is the number out of the A to D converter that's presumed approximately proportional to light intensity. And on the vertical scale are the numbers out of the lookup table, which go from 0 to 255. So that's an 8-bit code. So the point is that between codes is not much light down at the dark end, and between codes is more light, lower slope this way, up at the bright end. So if this was, you'd curve it the other way if you do the opposite of what I just said. But this is a compressive curve, which means that the slope is reduced at high intensity. The slope being reduced means that the increment horizontally in the light domain is greater. Right, so more light change to get one code when it's bright and less when it's dark because the noise is less in the dark. If there was no read noise and you had just shot noise, this curve would be a square root curve. And then to relinearize from 8-bit back to linear intensity, you'd use a squaring. And that's pretty close to what people use for gamma curves. But you can get an actual optimum curve. In fact, the optimum for the case of just shot noise plus an independent read noise is a square root curve that's been offset so that the origin is moved up a bit. You can find parts in catalogs, like here's from TI. They're talking about their digital still camera engine, and they show in the top of the figure the thing called an analog front end, which is any of various other parts you can attach there that does the correlated sampling, what they call automatic gain control, and A to D converter. I'm not sure what they mean by automatic gain control here. Typically there's a programmable gain amplifier under control of your software, but automatic tends to mean it automatically adapts to signal level, and I haven't seen cameras that work that way. It's automatic at some point, but it's, you know, that automatic control is deferred to the software. It's not in the analog front end chip. And then the digital still camera engine chip there has the image processing and image compression, and that's the bulk of what we'll be talking about in today's pipeline stuff. Yeah, question?
They showed a CCD and correlated double sampling in the analog front end. Is correlated double sampling done with CCDs typically?
Yes, with a CCD, the analog output can be alternating between a measurement of a zero charge bucket and a charge bucket with a signal, and the zero there is set by a reset so that you can do the off-chip cancellation of that reset noise. So all the charges are going through a single path, and you can do the CDS off-chip. With the CMOS, you can't do it that way. You have to do the CDS in the column amplifiers because the charge to voltage conversion was done back there. Well, actually, you don't have to. Yeah, it's complicated, but it's typically the way it's done. Okay, so there's a number of steps that are important to get the black level in the right place on a sensor. And this tends to mess up pictures if you don't do it right. So I talked about the black clamp in the A to D converter, but that doesn't give you an absolute black reference very well because the A to D converter doesn't know where the charge zero was of the sensor unless your CDS chip has a good absolute zero in it, in which case it might work. Very often you have a step called dark frame subtraction, especially with CMOS sensors, because with CMOS, each one of the pixel sensors itself has a transistor with an offset or a drift, a flicker noise, and so on that moves its zero around. So you get these fixed patterns due to the transistor offsets, and if you capture a dark frame and an image frame and do the difference between them, those will cancel out. And then there's what I call dark level drift adjustment. If between capturing the dark frame and capturing the light frame, the temperature of your sensor changed or something, because say you keep it cold normally and every time you turn on the camera to take a picture, it's warming up while you capture these two frames and there's a couple degrees difference, that may be enough to offset the two images with respect to each other. So you can detect that easily by looking at the dark shielded edge pixels and make sure that after you do dark frame subtraction, those edges go to zero. If they don't go to zero on average, you sense that average and correct for it. And then what is often a fairly large effect in images is the glare or flare that Ian talked about optically, and that's an offset due to all the stray light in your camera that's hitting the sensor. And that might be 1% or so of the average intensity of your image. So you might have another step that measures the average intensity of the whole image and subtract off 1% of that to try to get the black parts of the image near zero. Another thing that's done pretty early on the raw data is to adjust the gains of the pixels to account for the vignetting of the lens or the angle-dependent quantum efficiency roll-off of the sensor. So you have sort of a slowly varying gain across the image that's typically like a gain of 1 in the middle, and you boost the edges that have fallen off. You can represent that 2D varying gain as either a polynomial in X and Y up to some moderate order, 4th or 6th order, or something like that. Or you can represent it as a table, typically a sparse table over the image. You could also represent it as a gain for every pixel, and that would allow you to... Generally, it's not ludicrous to store everything you know, and that's what they do. But everything you know is really just a little bit of metadata on top of the image raw data. So you get the data from the sensor, that's the bulk of it, multiple megabytes. And then the metadata is just some strings about the camera settings or maybe the light meter reading and focus measurement if you have that. But yeah, generally the metadata will store pretty much everything the camera knows. Let's see, so after you do this spatially varying gain correction in the raw converter typically, or somewhere in the pipeline in the consumer camera, now you've got numbers that are proportional to the light intensity of the scene that you took a picture of. You've got black at number 0, so everything is just proportional, and that's a good place to be. Then you can start to do the real processing. Here's a figure out of a paper I found online. There's a reference to it in which they illustrate a very useful concept when you're thinking about designing pipelines for digital cameras. You kind of want to model what the camera does and then undo it. That is, like, pop the stack, go through operations in reverse order to undo what the camera did. So they show here an input processor that's undoing what the imaging array did, and that's like linearization and spatial gains. And then they show this color engine undoing what the color filter array did. So that'd be like interpolation to try to get back to an estimate of the color image that was here before you went through the filters. And then they show this anti-vignetting. Well, in this case, they've done they put the vignetting gain in association with the lens, of course. You could do this in different orders, but conceptually, you want to think about undoing what the stages of your camera did. So they've got the camera pipeline going right to left, and then the processing pipeline in corresponding stages from left to right. They haven't shown all the stages, all the details here that you're going to want to do, but this gives you an idea of a good way to think about how to undo some of the peculiar or non-ideal effects of your optics and your sensors and so forth. So another important step that you tend to want to do fairly early in the pipeline is to figure out what color off of your sensor represents white. That is, what ratio of red to green, or ratio of, well, you need at least a pair of ratios, like a red over green ratio and a blue over green ratio is one way to characterize it. What ratios there correspond to the colors that you're going to call neutral in this image? And it varies with what you're taking a picture of, because when you're outdoors under bright sunny sky, that's about a 5500 Kelvin illuminant. It's a different color than when you're in the shade, when you got more like 6500 Kelvin, you got a bluer light. Or if you're indoors under incandescent light around 3000 Kelvin, you have a very orange light. But in all of those conditions, if you're taking a picture of something, you want your photograph to show the color in a kind of a natural way. If you take a picture of a white piece of paper, you want that to reproduce as white in the photograph, or pretty nearly. So the camera has to figure that out pretty early in the processing. It has to know what color that the sensor measured are we going to call white for this particular photograph. So you can get that from an automatic white balance calculation, and I mentioned here gray world assumption plus. And the idea there, the gray world assumption, is you look at all the pixels in your image and you assume that white is the mean of all those. So you just sort of distribute all your colors in such a way that the mean color is neutral. It's not a great or wonderful way to estimate white, the illuminant color in an image, but it turns out it's very often as good as the much fancier methods. And so the plus there represents the fancier methods, which try to take this gray world method and improve on it. For example, you can detect large areas of sky and large areas of green in the foreground and things like that, and try to de-weight those in the average and thereby get a better estimate of where white might be. Or you can take manual white balance setting. If your camera's been calibrated, it's got settings on it for, say, daylight and shade and incandescent and so on, where you've predetermined at the factory, if you take a picture of a white thing under this illuminant, here's the color ratios you get. So you set it, and then the processing can proceed knowing what you've told it the illuminant color is. Now, at this point in the processing pipeline, you can apply channel balancing gains. That is, you apply some gains to the sensor red, green, and blue channel until the ratio of red to green, blue to green, and so on are equal to 1 for the thing you're going to call white. Question?
So if the calibration data is done at the factory, how does the picture know under what light conditions you took the picture?
So that's, if you're calibrated in the factory, how does the picture know the light conditions? That's what I meant by manual white balance setting here. So most of the cameras have a setting where you can declare what the illuminant is, at least the high-end cameras do. So you go into white balance, you either set it on auto, or you pick sunlight or cloudy or incandescent or whatever. So if you've declared what the illuminant is, the camera doesn't have to try to figure it out. It uses the calibration data to tell it what those ratios are.
Second light sensor, which looks at all that, looks all around to see what the average light is.
Right. Some cameras have a light sensor to look at the lighting. So if you have like a little light meter, a little white ball on your camera that light comes into from all directions, it basically just does an average of the scene that you're looking at, or of the light that's falling on the camera. It's not very much different from averaging the light in the picture that the sensor captured, and sometimes it could be much worse because, for example, you're taking a picture of a shady scene, but you're in the sun. It's going to be really messed up, or vice versa. You're in the shade and getting a lot of shade light, but the subject across the street is in the sun. So those sensors, they can be useful, but they are not necessarily better than the gray world assumption at giving you the right answer. Over here?
Why is it 18%
18% gray card, 18% gray?
Yeah, why is an 18% gray card 18% gray? That's a very interesting historical question, and I don't have the details of the answer here. There are papers I've read that have gone into that in considerable depth, and I can't answer it. Okay, so once we've figured out what color we're going to call neutral, we can apply the channel balancing gains, as I mentioned, so that now you have in your relatively raw data still, you have, if you have an RGB value where the three numbers are equal, that represents a neutral color. That's a convenience for some of the stuff that comes later. You don't necessarily do that at this stage, but some pipelines do. And then there's a step of optionally clipping highlights to white. If you have applied gains such that equal values means neutral, then you clipping everything to the same level will clip to white. A straight clip is not the best way to control highlights, but if you don't do something here, then regions that are too bright and the sensor starts to saturate are very likely to have one channel saturating before another, and they're gonna, the apparent color, if you process it without any care, is gonna be way off neutral. And you don't really want your bright highlights to come out pink, purple, blue, or whatever. You want them to come out white. So you have to do something about the overexposed highlights. Yeah, Jim?
Once again, is that done digitally or through analog?
Yeah, so we're way past the A to D converter. So okay. we're doing all this digitally. In older cameras, it's conceivable that you could do these gains and clipping in the analog domain. I'm not aware of any that do it that way, but there probably were some in the past. Yeah, Francesco.
Clipping done is part of the demosaicing?
Yeah, so is the white clipping done as part of the demosaicing? And yes, as it says here, second line from the bottom, optionally include highlight neutralization. So good question. If you haven't clipped the highlights already, in fact, when you've got only one of red, green, and blue at each pixel, you can't really do highlight clipping on the pixels independently because you don't have all three components, and so you really want to ideally integrate that with the demosaicing somehow. So this is where you take data that only has one color measurement per pixel and bloat it into three. So it's an interpolation within each color plane, or it's a extrapolation of data to fill out the RGB format that you're trying to process toward. There's a lot of different complicated algorithm choices here. Generally what they do, I mentioned this last week when I showed some aliasing examples, is that they tend to sacrifice resolution of chroma detail in an attempt to get better luminance resolution. That means if you assume that the chrominance, the color ratios, if you like, is only sort of slowly varying, then you can estimate it over neighborhoods. And if you've got it correctly estimated in a neighborhood, you can use that to get better resolution of luminance, close to as much as you would have gotten with a monochrome sensor if you've got the color correctly estimated. You don't have enough information, however, to actually get the color correctly estimated. And whenever there are sharp chroma edges, if there's a sharp edge and you assume it's varying slowly, then you will induce aliasing artifacts into the luminance that you've estimated. So there's all kinds of tricky things here about trying to estimate where the edges are and respect them so you don't corrupt them and so forth. This is a figure out of the Porolsky and Spalding chapter again that illustrates one simple example of an edge detecting algorithm where they go through some logic on the neighborhood comparing pixel differences to thresholds to try to decide if there's an edge there. And depending on whether there is and which direction it is, they do different averaging of pixels. Sorry. So I'm not going to get into the details of these algorithms. I just want you to know there's a lot of still active research in this area trying to find out what are the best ways to infer the missing values. Yes, hi.
What do you think? I mean, is that RGB sensor long-lived? I mean, will it be around in 20 years? Maybe that's a loaded question, but maybe not.
That's a loaded question. Let's don't get into that here.
Independent of phobia.
Yeah.
It can survive.
I think so. I mean, people are reasonably tolerant of the small kinds of artifacts that you get off those cameras, and if you have enough pixels and a strong enough anti-aliasing filter, the images are acceptable. So compute and apply the color matrix. So now, I mentioned this a couple of times, that there's sort of among the amateur aficionados of digital imaging, there's not really much awareness of this concept of color matrixing, but it's fundamental to getting decent colors out of a sensor, is that you have to go through a 3x3 transform to convert to an appropriate color space. Part of what you're doing there is to map the white point of your scene into the white point of the output color space. For example, if you use sRGB, that space is defined in terms of a set of primaries and a reproduction white point, where they say the reproduction white point is D65, which means approximately the color of a 6500 Kelvin black body. And they've defined it that way because they're thinking about monitors and reproducing pictures on monitors. But the scene you took a picture of might have been in 3000 Kelvin or 5000 Kelvin or whatever. So you got to map the white point, and we talked about how to do that with changing the gains, but that only gets the white point mapped, and then you also have to map all the colors around that and keep them in a decent relationship, and that's what this whole matrixing thing is about. And there's no perfect colorimetrically accurate way to do that, because in colorimetry you can quantify the exact color of what you took a picture of and what you're reproducing, but there's nothing in colorimetry that tells you what the relationships between those should be if the reproduction white point is different from your illuminant color. So you have to do some psychophysical experimentation to find out good mapping algorithms, and those usually get reduced to a 3x3 color space transformation at some point. So you want to preserve relative colors and preferred color rendering. And so this preference idea is not just getting the colors mapped right, but it's getting them rendered in a way that you like. And that means usually for most things, you want your photographic image to have more color saturation than your original scene. You want it to really pop. In many cases, there's an intermediate color space used. For example, the LMS space, which stands for long, medium, and short, referring to the wavelength sensitivities of the cones in the human visual system. Or the RIM RGB, which is a reference input medium metric color space that Kodak developed for this purpose. So in these intermediate spaces, if you just scale the three primaries, you get a pretty good color white point adaptation. So if you transform into one of these spaces, do just a diagonal transform, that is, just scale the three primaries to get white where you want it, and then transform back to the space you want to be in. That's a reasonable way to do white point adaptation. Yeah, Lance?
Brian Wandel at Stanford has made some claims about being able to reproduce color more accurately if you have 4 or 5 primaries. Is there any leverage in using 2 different greens in a Bayer pattern to try to get better color reproduction?
Yeah, excellent questions. Lance points out that Brian Wandel at Stanford has said you can get better color accuracy overall by using more than just 3 primaries, for example, 4 or 5. And could we get an advantage by using 2 different greens in the Bayer pattern to get more color accuracy? And yeah, you can. In fact, that was what Sony tried to do with their sensor that replaced one of the greens with what they called emerald. It's a slightly different spectral sensitivity curve. There's a lot of problems in doing that, like all of the standard work on demosaicing algorithms doesn't apply anymore. If you're trying to get better chroma information, you're going to have to give up some luminance detail to do it, or you're going to risk more kinds of aliasing. So yeah, you can get better color, but it's not easy and it's not often done. Yeah, Jim?
You seem to be implying that most of this is linear transforms, or
this is linear.
Non-linear?
This is linear that I'm talking about, a completely linear transform. It doesn't necessarily have to be linear, but it almost always is because that's what's understood. So here's an example of a matrixing operation. If we had a color specified in XYZ space, which is the CIE's sort of primary lingua franca of color spaces, that everything's generally defined with respect to it, and we wanted to convert that color to sRGB, the sRGB color space comes with a a standardized definition of the matrix that does that conversion. Now this assumes that the white point is already at the correct location in XYZ space, so there's no illuminant adaptation possible in this matrix. It's just a fixed matrix. I've put a box around the top row of that matrix. Those are the weights that, you know, when you do matrix multiply, you take a row of the matrix times a column of the thing on the right, and you do a dot product, which is the sum of pairwise products. So that means 3.24 times x minus 1.5 y plus half a z, or minus half a z, essentially. So that defines the red value in the sRGB space. sRGB is a nonlinear space, so we've got the subscript linear on the R here just to remind us we're not really in sRGB yet. We're just looking at linear data. If you put in a neutral value, or say you want to get out a neutral value, you want to get out R, G, and B equal to 1. You can invert that matrix and find out what XYZ value going in would have given you that, and I've shown it here, and it's 0.95 on the X, 0.9999 on the Y, and 108 on the Z. That's because the third component, the Z, is a little bigger, that's a kind of a bluish color. That's what D65 is. It's kind of a bluish white, like on your monitor. Now, the color triangle I've drawn here in the XY space, and I've put the formula to remind you that XY is just a projection of XYZ in which you've normalized by the sum of the components to get a chromaticity without respect to intensity. The color triangle there is the region where all three of R, G, and B are non-negative. And so the edge that I've pointed out with the blue line there where it says R equals 0, that's the edge of the triangle where the red component goes to 0. So there's some interesting relationships you can notice between these matrices and triangles and so on. So that edge is defined by that equation where red equals 0 equals that linear combination of X, Y, and Z. So it's easy to work out where that edge is. And there's no explicit representation here of what the primary colors are that are used by this sRGB space, but if you look at the picture, you can see that the red primary over here is defined by the edges. This is the blue equals 0 edge, and this is the green equals 0 edge. So the row of the matrix that defines the red has nothing to do with the red primary, but the red primary is defined by the other two rows of the matrix. So there are these kind of dual relationships between matrices and primaries and so forth. So when you look at a camera pipeline, you tend to have these structures that Peralsky and Spalding call the LUT matrix LUT approach. This is like simple overall pipeline for taking camera data and getting it into an output color space. So the camera data, they show it going through a nonlinearity here, which is typically actually a linearization to make the data linear. And then there's a matrix, and then there's a lookup table on the output. The matrix in the middle, they've shown factored into 3 parts. And the one I just showed you is this one called the XYZ D65 to sRGB matrix. And then that assumes that you've done something in between that to do, or before that, to do chromatic adaptation to get the color that you want to call white to map to the D65 point in XYZ space, and then something before that to to take account of the color sensitivities of the camera itself. These are all 3x3 matrices, and so they compose together into a 3x3 matrix. And what the camera software typically does is it treats these things in a factored way, so you can sort of reason about the different parts of it, and then it composes them all together, and it actually runs the data through a single 3x3 matrix transformation. There are some cases where a pipeline will have more than one matrix transformation and do some explicit operations in an intermediate color space in between them. So after that matrixing, there are these lookup tables where they've shown a single lookup table factored into 2 parts. There's a tone scale lookup table and an sRGB nonlinearity. Yeah, question?
All right, so I hesitate to bring this up. So whenever you do matrix math, there's a question of resolution. And does any of that, or how much of that do we see as users of this technology?
So there's a question of resolution, you say, and I assume you don't mean spatial resolution here. You mean like the numeric accuracy, right? And so these calculations are generally done in like 16-bit space or some reasonably high bit depth, wide dynamic range space, sometimes floating point. At the end, you're going to want to get back to an 8-bit number, but you want to keep all your intermediate calculations with a few extra bits, both for kind of headroom and overflow issues and noise issues and so on. And sometimes you may store or cache intermediate results in a processing pipeline so that subsequent adjustments can be very fast. So you need plenty of dynamic range if the decision about how bright to render your picture hasn't been made yet. Okay, here's a tone rendering nonlinearity, or an S-curve. They showed, again, a lookup table that had two different functions, and this is the first part of that function, and I emphasized this again in some of the earlier lectures, that this is a step that's very often forgotten when engineers and amateurs look at digital imaging, because they haven't been steeped in the lore of photography from the last 100 years where this was an important function. It was part of what photography is all about, is mapping the range of tones into something that makes a nice looking photograph. You don't want to just take linear data, represent it as sRGB and stick it out and claim you're done. So in particular, this the top of the S-curve, which takes a wide range of bright highlights and rolls them off. This automatic mouse thing is a pain, huh? That's pretty important to get a wide range of bright areas in an image to roll off nicely. Let me just see if I can cause my mouse to stay here. Yeah. And then in the middle of this curve, it's kind of, it's curved upwards here. You can see that's what we call an expansive nonlinearity. It means the more signal you have, the more gain you have. It's kind of almost like a square law thing. Not quite that steep, but that indicates a gamma greater than 1, meaning that you get some contrast boost. Whatever the ratio of intensities was in your scene, you're going to get a greater ratio than that in your reproduction in that region. And then down at the bottom, it's lower slope again, and that's to kind of make a soft landing into black and reduce the shadow noise, and again, make a good looking picture. So these characteristics of the toe of the curve, the so-called straight line portion, which is actually a it's actually not straight, but it's straight on a log-log curve if it has a gamma to it, and then this rolling off on the shoulder. These are all important aspects of tone rendering, and typically they have parameters that adjust them. In a raw converter, these parameters may be brought out explicitly to the user to play with sliders or something, or in a consumer camera, they're either fixed or they're made to be automatically adaptive to the histogram of the scene. So you can detect certain scene types, and you can say, this looks like a high-key shot, and this is a low-key shot, or this is a portrait or a landscape or something like that, and put in different strategies for how to render that to make a good photograph. Yeah, Valdemar?
Does sRGB by itself have a gamma curve, or is it linear?
Yeah, does sRGB have a gamma curve? Yes, it does, and so that'll be next. So that's the second half of this LUT in this picture, is the sRGB nonlinearity, and let's see if it's coming up next. No, it's not quite here yet. We'll get to that in a minute. Actually, I don't even know if I have a picture of it, but I showed it in a previous talk. That sRGB has its own gamma that's not exactly it's not a pure power law type gamma, but it's a two-part piecewise power law kind of thing. This is just an example to show that you may have more than one of these LUT, matrix LUT kind of structures, and they're connected in the middle with an intermediate RGB space. And these guys at Kodak developed a couple of spaces they called RIM and ROM for the reference input medium metric and reference output medium metric RGB color spaces. So reference input means it's a scene referred color space. The intention there is that the numbers in that space represent the intensity ratios in the scene that you took a picture of. And reference output means that the numbers there represent the intensities of the photographic reproduction that you're making. And so it's in getting from the input referred space to the output referred space that they do the rendering, and they chose the space in such a way that it's a good place to do that rendering. It's both a good place to do white point adaptation by scaling the primaries, as well as a good place to apply tone rendering curves. So you get into this space, you mess with your data to get it the way you like it, and then you convert to the output color space you want. So that's two of those lookup table, matrix lookup table structures. And then it's not my last slide, but this is the finish up step of the processing pipeline. Is basically you matrix it to the final color space that you've chosen for your output. A lot of cameras nowadays have a choice there that you have to make. You can use sRGB, or you can use Adobe RGB, or sometimes you can use others. Some of them have other choices where, in addition to choosing the output color space, you're also changing the kind of color rendering preferences. You can choose vivid or muted or something like that. It doesn't change the color space you're going to, but it changes the matrix because you have different color rendering preferences. In a raw converter, it's the same thing. You may render it to sRGB for viewing on your screen and then render it to Adobe RGB to put it out to a file, or you may render it to some space that your computer's built-in color management software can take care of re-rendering to a different space depending on whether you want it to your screen or your file or whatever. And these color spaces have not just different primaries and different matrices associated with them, but also different gamma nonlinearities. For example, on the Macintosh, the Apple RGB and Color Match RGB and things like that have a gamma 1.8, and on the PC, the popular color spaces have a gamma 2.2. Actually, I've forgotten what Adobe RGB is. It's one or the other. And then you save it to a file, sometimes uncompressed as a, well, reduced to 8 bits, but otherwise uncompressed, or sometimes even 16 bits as a TIFF file, or you compress it to a JPEG. Next week, is it next week that we're having Ashok talk about lossy compression? I think it is, so there'll be some logical sequence there. If you go to JPEG, there's actually another color space conversion involved, where there's another 3x3 matrix that takes RGB and matrixes it to what's called YCBCR. So the Y there is the luminance component. It's not exactly the same as the colorimetric Y, because here it's a linear combination of things that have already been gamma compressed. So it's a linear transformation in a funny nonlinear space. But you get this thing they call Y, and then you get the red and blue chroma components. The red and blue chroma components are sometimes subsampled and to get better compression that way. And the three components are more nearly independent of each other, so they encode, they compress independently reasonably well. So this notion of 3x3 linear transformations is all over the processing pipeline, and the notion of nonlinear lookup tables is as well. But there's a lot of other steps sprinkled in at various places, and there's no kind of standard place to do noise reduction. You kind of do it wherever you can. Usually that's a nonlinear filter. If you do a linear filter, like a smoothing operation, you can reduce noise, but you give up too much signal. You lose a lot of sharpness, and nobody wants to do noise reduction by having their images just come out blurry, so that's not too good. But with nonlinear filters, you can do more clever stuff. There's a family of filters called rank-conditioned rank selection filters, which have interesting nonlinearities, and I'll give you a couple examples of that. And on the next slide, I think, there's a median filter, which tends to be a little bit harsh on photographic images, but is sometimes used. There's despeckling, which is sort of the gentlest possible RCRS filter, and there's a bunch of things in between. Or you can do a smoothing operation where you limit the amount to which any given pixel value is moved by the smoothing, so that in areas that are only have small fluctuations, the fluctuations go away, and when there's a big edge, the big edge gets preserved. And Lance was smiling because he knows he's the guy that taught me how to do this. Through a technique called dequantization is where I learned about this, and then I kind of applied it to things where it's not really doing dequantization, but it's the same kind of algorithm. You want to make an output that's consistent with the input. So if you have an estimate of the noise in the input or the quantization of the input, you want the output to be consistent with that, in the sense that no pixel value moves by more than, say, the noise standard deviation. And that works really quite well. And there's a lot of things like it called coring. Coring is another approach that does a very similar thing. And in general, there's this class of things called edge-preserving smoothers, many different ways of going about smoothing away noise while preserving sharp edges. And they work in varying degrees. And if you look at images from different manufacturers and kind of noisy situations and look at the shadow detail and so on, you get very different feelings from different cameras based on what they've chosen to do there. Sometimes they get very smooth and pasty in the shadows, and they still have sharp edges. And sometimes you get kind of a watercolor painterly effect between sort of these discrete brushstroke looking things. The other thing you can do there that helps a lot and is pretty common in consumer camera processing pipeline hardware is a luma-dependent chroma gain reduction. So that means in the dark areas of the image, desaturate the chrominance. Get rid of the color noise when you're in the shadow area where it's it's too noisy to keep good color. So these kinds of steps get sprinkled in wherever it's convenient in the data pipeline. Here's the example I said I was going to show you on the rank conditioned rank selection filters. So the idea is you take some neighborhood, most typically just a 3x3 neighborhood, and you sort the 9 pixel values in that neighborhood. You rank them. And then you look at what rank is the center pixel. And then depending on what rank it is, you select some other rank out of your sorted list as the value for that pixel. So a median filter isn't always characterized this way, but it's one extreme version of this. You sort all the pixels, and then no matter what the rank of the one in the center is, you replace it with the one of rank 5. So you always replace each pixel by the median of its neighborhood. The despeckle filter is a thing that in most cases doesn't change the pixel value. So if the rank of the pixel in the center is anywhere from 2 through 8 out of the 1 through 9, you just leave it alone. But if it's rank 1, you replace it with the rank 2 value, and if it's rank 9, you replace it by the rank 8 value. So that'll take things that are outliers, and it will move them just enough that they're no longer outliers, that they're no longer outside the range of their neighborhood. That's if you have like random bit noise in your data, it makes a lot of these pixels that are too big or too small for their neighborhood. This will pretty effectively knock them out. And it's not very smart, but if the numbers of such things are fairly small, this is a pretty effective way to reduce them to where you probably won't notice them. It can do damage to the pixel, the image structure in some cases, but it's usually not bad. Yeah, so are you doing it with R, G, and B independently? Yes, you can do that on the raw data before demosaicing with some kind of a neighborhood and bare mosaic space, or you can do it after demosaicing, and it may be less effective. I don't have that much experience with how to do this with Bayer cameras, actually. So. Okay, there's other optional steps that can go in there. The pipelines where the guy was undoing the effects of the camera stages showed a lens distortion correction. That's one I haven't talked about, but you may want to do an operation that's not affecting pixel values locally, but it's actually moving them around and distorting the whole image. So you can have a lens that has distortion and you can undo it, or you can have a lens that doesn't have distortion and you can distort the image for some other purpose. For example, to link up multiple images that are perfectly rectilinear into a panorama, because you're shooting at different angles, the rectilinear projections don't really line up. So if you map each of those to a cylindrical projection, then you can stitch them together and make a panorama. Or you can warp each one to a different, same rectilinear projection, say. So there's a lot of image warping stuff that goes on in a pipeline somewhere, especially if your camera's supposed to do panoramas. There's the high dynamic range remapping kinds of steps. Some of these are based on Edwin Land's Retinex model of perception, where he has a particular way of preserving local contrast while doing adaptation in a way that has the right kind of long-range correlations and so on. That's one approach people often use to designing these algorithms. It works pretty well. And if you've warped your images to make a panorama, you still have to worry about exactly how to get the edges lined up and blended. So the idea of slowly varying intensity gain in a high dynamic range mapping can be integrated with the kinds of intensity adjustments you need to bring the edges into agreement in a panorama stitching. And besides just adjusting the gains of the images to make them line up, you can also adjust the colors on a slow, continuously varying process. And that's part of Land's Retinex theory as well, is how we can spatially adapt to colors, so that when you're looking at a sunny area here and a shady area here, your eye kind of adjusts to those, so that if there's something white here and something white there, you don't really notice that one's yellower and that one's bluer. They both just look white. So you can do that in your images as well, so that the white objects in those different lighting environments actually do render to the same neutral color, if that's what you want to do. Here's an example of a high dynamic range rendering problem. Again, from the Perelsky and Spalding chapter. They show the same photograph rendered dark and rendered light, and on the bottom we have the histogram of the different light values of those images, and a couple different ranges that they've rendered. And this is one reason why automatic rendering of images is so hard. If you have a computer program that looks at this histogram and tries to figure out how to render it to make a pleasing photograph, it doesn't know that those are your favorite people are in the foreground or your favorite mountains in the background. It doesn't know what part of that picture you care about. So it can compress all that range and give you a low contrast image, but that's not really a very useful result. So you really need these nonlinear local operations to bring down the gain in the bright mountain area and bring up the gain in the foreground, and try not to introduce spatial artifacts in the way the gain varies between them. And they've done that in the book. I didn't think it would be worth projecting that image here, but there's some nice color plates to illustrate some of these algorithms. And if you want to see the book, come find me. So there's a lot of big topics in all this, and we just had, you know, broad brush treatment in an hour, but well, there they are. I think we'll just leave it at that and go for questions. Thanks. Questions? Okay, Valdemar.
On the last slide, we have dynamic range photo, or that's essentially just playing with the curves in Photoshop.
Yeah, is this essentially just playing with curves in Photoshop, you ask, right? Well, it's not. You can't do it that way. There's no way. So if all you have is curves in Photoshop, you can reduce all of this dynamic range, to one low contrast image, but you can't get high contrast in the foreground, high contrast in the background at the same time with one set of curves. If you could segment the image and apply one set of curves in one place, one set of curves in another place, then you could do what the high dynamic range rendering does, but then you have to worry about the boundary between those segments. And that's what the Retinex algorithms try to do, is they try to bring up the gains where it's dark, take the gains down where it's bright, and make a transition between them that doesn't give you visible artifacts. Yeah, question back there?
Could you do similar things by sort of taking a sort of frequency approach to the image and just remove the low frequency parts of the image?
Yeah, so the question is, can you use sort of a Fourier approach and frequency analyze the image, take out the low frequencies, and then crank up the gain on what's left? And yeah, in fact, you can. And that approach was pretty well developed actually in the 1960s by Al Oppenheim and Tom Stockham in a paper they wrote called something about visual models and image processing. Sorry, I don't remember the title right off, but what they showed, and they actually developed this whole theory of homomorphic signal processing, homomorphic image processing, and what they showed is that since the lighting that varies slowly is multiplying the fine structure of your image, you want to separate a low frequency thing from a high frequency thing when they're in a multiplicative relationship. You want to convert to a logarithm, a log image space, so that in that space the low frequency and high frequency are additive, and you remove some low frequencies, convert back. So yeah, filtering techniques in a log domain is one way to do this. It's well studied, well developed, has nice theory behind it. It's not the best approach, but it's a good starting point. Yeah. Anybody else? Yeah.
It seems like, you know, this is one part of the problem. I mean, maybe another part of the problem is that the sensor, you know, may not have the dynamic range to even get that curve, so that you could apply these algorithms to it, as opposed to film, which seems to have dynamic range. Is that the case?
Yeah. Yeah. So Hai points out that you have to get the dynamic range at the sensor before you have any hopes of processing it this way, and film may have better dynamic range than digital. I think digital can have enough dynamic range. In a DSLR, big pixels and shot at a reasonable ISO, you've got probably more dynamic range than you can get with a lot of film. You may have, maybe not quite as much as you get with some color print films, but close. Your dynamic range will, when the dynamic range is high, the thing that limits it is going to be usually the lens flare, the stray light in your camera that pollutes your shadow regions. And when you're in that region, that puts a finite limit on how much dynamic range the camera has to capture or can capture, whether it's film or sensor. So the low-end cameras, you're right, you probably don't get enough dynamic range to really need this kind of thing very much, but in the high end, most DSLRs get pretty good dynamic range, probably about as much as you're going to get with film.
Let me ask it a different way then. If you look at the average, amateur, processed picture, going back 15 years, there was much less, what's the word again, where areas are solid white, no highlight detail. It seemed like there was much less of that.
Less blowing out of highlights in average amateur pictures 15 years ago.
Today for the given.
Yeah, well, part of the problem is that a lot of the camera companies don't do an aggressive job of rolling off the highlights when they do the rendering, and Nikon in particular tends to have kind of a clipped highlight look. So you do get these big white blown out highlight areas in pictures, and that's something that film was particularly good at. It had a very long shoulder on the curves. So I think it's not so much a question of total dynamic range as it is a question of how people have chosen to render the images.
What color channel fits first so you get these post-visualization color highlights?
Yeah, if one channel clips, then you've got trouble. So yeah, and so you got to be careful with the exposure. And film is better at the high end at maintaining reasonable behavior when it's overexposed, whereas a sensor, once you hit clipping, there's not much you can do there but render it to white. Yeah, Lance?
There are some kind of fancy sensors that try to get around that. They have little dodges of one kind or another.
Right, you can invent all kinds of schemes for getting around it, like Fuji's 2 photodiodes per pixel scheme, where they measure with the small pixel, they try to get measurement of what's going on up in those highlights where the main pixel is saturated. And there's other techniques like that. In my impression, they don't work all that great, but we're going into screensaver mode, yeah.
So there's more here going on than I ever had a clue about. How do you try to understand what's going on when looking at consumer reviews and as just an end user?
Yeah, how do you understand like reviews of consumer cameras given that all this magic is going on? Well, that's a good question. I'm trying to arm you with some knowledge so that when you read about these things you can interpret them better, but it's hard. The guys that are doing the reviews don't typically understand all this stuff, and so they have their own mental models of what's going on, and sometimes they say things that only make sense in their own imaginary world. So. Okay, thanks.